In this video, we're going to look at one application of using our polynomial function. And the problem we're presented with here is you need to construct an open box from a square piece of material that is 36 inches on a side. So basically what we have down here is our square piece of material where it is 36 inches on each side. And it says we want to construct an open box from this square piece of material, 36 inches on the side, by cutting equal squares. We want to cut equal squares with sides of length x from the corners and turning up the sides. So here you notice we've labeled, we want to cut out a square from each of the corners. And once we cut that out, we can fold along this dotted line here, 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 and here. If you fold up the four sides, then you will end up with an open box that's shown here on the right hand side. So to do that, we want to write a function of the volume V that represents this box. So write a function V that represents the volume of the box. Well, we know that if we're trying to find the volume of this box, then volume is equal to the length times the width times the height. So we know that the total length of the square piece of material is 36. Well, if all the way across is 36, now keep in mind, what are we doing here on the corners? We're cutting out this square, so that means we're cutting out this part, which is x, and then also on this side. So that means there's also an x here, here. So all of these, we have a length of x that we're cutting out as we go around. Well, if we cut off this x here and this x down here, then what is this distance? Well, if the total distance is 36 and we're going to cut off an x at the top and an x at the bottom, then you're left with 36 minus 2x. And the same thing is going to be true from here to here. We cut the x off the left, the x off the right, all the way is 36. So this is going to be 36 minus 2x. So what we're saying is, whoops, not 3x, this is 36 minus 2x. So 36 minus 2x is across the bottom here. And then on the side, this is also 36 minus 2x. And again, if we have this square piece of material, then we're going to end up with kind of this square box. So there we have the length and the width is 36 minus 2x. Then what is going to be the height? What's going to be the height of this box? So if this here is the height, how tall is this box going to be? Well, over here, notice we're going to cut out x. We're cutting into the material x. So that tells us this here is x. So if we fold the box up, then the height of the box is simply going to be x, the amount of material that we're cutting out of the corner. So then the volume is going to be equal to the length, which is 36 minus 2x. 36 minus 2x. The width is also 36 minus 2x. And then the height is x. So we could certainly just write this as 36 minus 2x quantity squared multiplied by the height of x. So this here is going to give us the volume of this particular box. All right, now here's the important part. If this is the volume of our box, then the part B says determine the domain of our function. What is going to be the domain of this function? Well, if we quickly look at the function, we're like, well, we can multiply any number by 2. So we have 36 minus 2x. So if you plug a number in for x, we can multiply anything by 2, and we can square anything. So it looks like your first thought might be x can be anything, all real numbers, because we can plug any value in for x. There's nothing that's going to make this function undefined. But when we start thinking about this function as representing the volume of a box, then that's going to be a little bit different. Because remember, if we think about this in relationship to the box, what is x? X is our domain. Well, x is the amount of material that we're going to cut. Well, if we don't cut anything out of the corner, we don't have a box. So therefore, we know that x has to be greater than 0. And x can't be negative because we can't have a negative value. We got to cut something out of the box. So I think it's obvious that x has to be greater than 0. Now, can x be anything greater than 0, or do we have a limit? Well, if the box, the piece of material that we start with is only 36, then if it's only 36 inches, then that means we have to have something smaller than 36 inches, right? So you may think and say, well, that's correct. Well, keep in mind though, if we cut in from one side 36, we've already cut all the way across. So the question is, we can only cut halfway, or we really can't cut halfway. It's got to be less than halfway, because if we cut x in from the left, we also cut in a distance of x from the right. So let's look at an easy way we can figure this out. What we're really saying is, if the volume is equal to 36 minus 2x squared, then we know that this amount here, 36 minus 2x, cannot be equal to 0. So if I take 36 minus 2x, set that equal to 0, and if we solve for x, add 2x over, and then we can divide by 2, so we have 36 divided by 2, so x is equal to 18. When x is equal to 18, then that's going to give us 0. Well, if x is equal to 18, again, that means we're going to actually cut 18 inches from the left, 18 from the right, so we've cut completely through the box, so there's nothing left for us to fold up. So what that tells us is x has to be less than 18. So we have x has to be greater than 0 and x has to be less than 18. So our domain would be, we could write this as 0 is less than x is less than 18. And what this is basically telling us is our domain, our x value, has to be between 0 and 18, because that's the amount of material that we can possibly cut out. Now, part C kind of leads into how much do we want to cut out? Well, if we want to use the function v to determine the value of x that will maximize the volume. So what value of x, how much material do we want to cut out of the corner so that we will have a box that will give us the maximum volume? So how can we go about doing that? Well, we can take our function. We know the function is v equals 36 minus 2x squared multiplied by x. Now, what I would recommend here is actually looking at the graph of this and putting this into your calculator and looking at the graph. Now, keep in mind, when you go to put this into the calculator, you're going to have to make sure that we have the correct viewing window. And we already know, based on part B, our domain, which is our x value, has to be from 0 to 18. So we're only concerned with part of the graph going from 0 to 18. Now, of course, this graph is going to continue on down below or larger than 18 and where x is less than 0. But because we're looking at the box, we're only concerned about 0 to 18. Now here, you're going to have to play around with your window a little bit to figure out how high do I need to go on the y-axis. Well, keep in mind, what does this represent? The y-axis is representing the volume. So this could be a rather large number, and you can play around with this, and maybe before I tell you, maybe you want to pause the video to see if you can figure this out on your own looking at the calculator. But if you play around with this enough, realize that you're going to be multiplying the length times the width times the height. You're going to have possibly a rather large number. And this is going to actually be, I think you want to use somewhere around maybe 4,000. And if you look at the graph of this is going to go up like a parabola, and then it kind of slopes off a little bit. And let me see if I can draw this a little bit better. It's going to go up and then slope a little bit here to the right. And if we're looking for the value that's going to maximize this, then that means we want to know this point here. And more specifically, this is our maximum point. We're looking for what x value is going to give us this maximum point. Now, using the calculator, you can go into the way we looked at it before. You can go to second function and trace. And you want a second function trace or a second function calculate. And we want to calculate the maximum. So you would go in and select maximum. Then you would select the left bound. And remember, when you do that, you're going to put a little arrow when you select the left bound. And then the calculator is going to ask you to do the right bound. And you would go to the right of this point, hit enter, and you have your other arrow over here. And then your calculator is going to say guess, and you're going to move it close as you can. And then your calculator should tell you that you're going to end up with x equals 6. So when you get x equals 6, that's going to give you the maximum volume. So x equals 6 inches is the amount that we want to cut out of the corner of our material to have the maximum volume. So if we cut in 6 inches and 6 inches, that's the square piece that we want to cut out so that we will maximize the volume of this box. Now, if we do that, that gives us x equals 6. Now, what are the other dimensions? Well, this is the height of the box. Well, if we plug 6 in here, we would get 36 minus 2 times 6. So that means we would have 36 minus 12. And 36 minus 12, we're going to end up with 24. So what that tells us is for our box, we're going to have 24 by 24 because we know the length and the width are going to be the same. And then, of course, the height is equal to 6. So here we would end up with a box that is 24 by 24 by 6, and that would give you the maximum volume. And if we want to find the maximum volume, then all you'd have to do is multiply 24 times 24 times 6, and you get 3,456 cubic inches. So if you were actually wanting to know the volume, that would give you the volume of this particular box. And of course, on the graph, that's going to occur right here. This high point is going to be 3,456. That's going to be the y-coordinate from this graph, because if you look at our function, v is over here representing this. So this point, our maximum point here, is going to be the x value, and then v is representing our y-coordinate. The v is the volume, which is the 3,456 cubic inches. So that means it's going to take 3,456 cubes that are 1 inch by 1 inch by 1 inch.